Unit 5, Elementary Probability Objectives. Having studied this unit, you should be able to understand the elements of probability, calculate some probabilities of events associated with random experiments, apply the concept of probability in some biological phenomena. 5.1 Introduction. Without some formalism of probability theory, the student cannot appreciate the true interpretation from data analysis through modern statistical methods. It is quite natural to study probability prior to studying statistical inference. Elements of probability allow us to quantify the strength or confidence in our conclusions. In this sense, concepts in probability form a major component that supplements statistical methods and helps us to gauge the strength of the statistical inference. The discipline of probability, then, provides the transition between descriptive statistics and inferential methods. Elements of probability allow the conclusion to be put into the language that the science or engineering practitioners require. An example follows that will enable the reader to understand the notion of a p-value, which often provides the bottom line in the interpretation of results from the use of statistical methods. 5.2 Definition of some probability terms. Definition. 5.1 Random experiment is an experiment in which the outcome cannot be determined or predicted exactly in advance, i.e. it is the process of observing or measuring the outcome of a chance event. Some of the characteristics of a random experiment are all the possible outcomes of the experiment can be specified in advance. The experiment can be repeated indefinitely. There is a sort of regularity in the outcomes observed in large repetitions of the experiment. Examples of random experiments includes throwing a fair coin and observing the outcome, throwing a fair die and observing the number on the top face, taking a student at random from science class and noting the sex of the student. All of these examples satisfy the above characteristics of a random experiment. Definition. 5.2 Sample point, outcome, the individual result of a random experiment. Sample space, the set containing all possible sample points, outcomes, of the random experiment. The sample space is often called the universe and denoted by S. Event, the collection of outcomes or simply a subset of the sample space. We denote events with capital letters, A, B, C, etc. Example. 5.1 If an experiment consists of flipping of a coin once, then S equals H, T, where H means that the outcome of the toss is a head and T that it is a tail. A equals H represents the event of head occurring. 2. Example. 5.2 If an experiment consists of rolling a die once and observing the number on top, then the sample space is S equals 1, 2, 3, 4, 5, 6, where the outcome means that I appeared on the die. I equals 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 and 6 are elementary events, i.e. events consisting of a single outcome. Let A represents the event of an odd number will occur, then A is simply the set containing 1, 3, and 5, i.e. A equals 1, 3, 5. Review of set theory. Concepts of set theory are important in understanding probability. Given A, B, and C are events associated with a sample space S and omega represents an elementary event, outcome, in S, then the following are some useful definitions and results in set theory. Definitions. 5.3, 1. Union, the union of A and B, a UB, is the event containing all sample points in either A or B or both. Sometimes we use A or B for union. 2. Intersection, the intersection of A and B, is the event containing all sample points that are both in A and B. Sometimes we use A or A and B for intersection. 3. Subset, if for any omega A, then omega B. Then AB. 4. Empty set, if a set A contains no points, it will be called the null set, or empty set, and denoted by. 5. Complement, the complement of a set A denoted by AC is the set where omega S, omega AC but, omega A. 6. Mutually exclusive events, two events are said to be mutually exclusive, or disjoint, if their intersection is empty. I.e. A and B equals. Subsets A1, A2, are defined to be mutually exclusive if AI and AJ equals for every I is not equal to J. Theorem. 5.1 Important elementary set theory results. I, OB equals BUA and A and B equals BNA2, O, BUC, equals, OB, UC and AN, BNC, equals, INB, NC3, AN, BUC, equals, INB, U, INC, and O, BNC, equals, AUB, N, AUC, 4, AC, C equals AV, an S equals A US equals S, IN equals, and AUA equals A6, AUB, C equals AC and BC and, INB, C equals AC UBC. 5.3 Counting rules. Combinatorics refers to the methods used to count things. If a sample space contains a finite set of outcomes, determining the probability of an event often is a counting problem. But often the numbers are just too large to count in the 1, 2, 3, 4 ordinary ways. For example, if you put a grain of rice on the first square of a chessboard, then 2 grains on the second square, 4 on the third square, and continue doubling until all 64 squares are filled, how many grains of rice would you have in all? The number is so large that it is difficult to handle without a systematic enumeration technique. In short, to assign probabilities for an event, we might need to enumerate the possible outcomes of a random experiment and need to know the number of possible outcomes favoring the event. The following principles will help us in determining the number of possible outcomes favoring a given event. 3. Theorem 5.2 Addition principle. If a task can be accomplished by k distinct procedures where the ith procedure has ni alternatives, then the total number of ways of accomplishing the task equals n1 plus n2 plus nk. Example 5.3. Suppose one wants to purchase a certain commodity and that this commodity is on sale in 5 government-owned shops, 6 public shops and 10 private shops. How many alternatives are there for the person to purchase this commodity? Solution: total number of ways equals 5 plus 6 plus 10 equals 21 ways. Theorem 5.3. Multiplication principle. If a choice consists of k steps of which the first can be made in n1 ways, for each of these the second can be made in n2 ways, and for each of these the kth can be made in nk ways, then the whole choice can be made in n1.n2, nk ways. Example 5.4. If we can go from Addis Ababa to Rome in 2 ways and from Rome to Washington, D.C. in 3 ways, then the number of ways in which we can go from Addis Ababa to Rome to Washington, D.C. is 2x 3 ways or 6 ways. We may illustrate the situation by using a tree diagram below. Example 5.5. If a test consists of 10 multiple choice questions, with each permitting 4 possible answers, how many ways are there in which a student gives his/her answers? Solution: there are 10 steps required to complete the test. First step, to give answer to question number 1. He/she has 4 alternatives. Second step, to give answer to question number 2. He/she has 4 alternatives. Last step, to give answer to last question. He/she has 4 alternatives. Therefore, he/she has 4x 4x 4x, x4 equals 4 10 ways or 1, 0 48, 576 ways of completing the exam. Note that there is only one way in which he/she can give correct answers to all questions and that there are 310 ways in which all the answers will be incorrect. Example 5.6. A manufactured item must pass through 3 control stations. At each station the item is inspected for a particular characteristic and marked accordingly. At the first station, 3 R A R W W W W Dubs are possible, while at the last 2 stations 4 ratings are possible. Hence there are 48 ways in which the item may be marked. Example 5.7. Suppose that car plate has 3 letters followed by 3 digits. How many possible car plates are there, if each plate begins with a H or an F? 2x 26x 26x 10x 10x 10 or 1, 352, 000 different plates. Definition 5.4. If n is a positive integer, we define n equals n, n1, n2, 1 and call it n factorial, and 0 equals 1. Permutations. Suppose that we have n different objects. In how many ways, say in Pn, may these objects be arranged? Permit. For example, if we have objects A, B and C, we can consider the following arrangements: ABC, ACB, BAC, CA, CAB, and CBA. Thus the answer is 6. The following theorem gives general result on the number of such arrangements. Theorem 5.4. Permutation I. The number of permutations of n different objects is given by nPn equals n. 2. A permutation of n objects, arranged in groups of size r, without repetition, and order being important, is n. Rn npr. Example 5.8. Suppose that we have 5 letters A, B, C, D, I. What is the number of possible arrangements of these letters taken all at a time? 2. What is the number of possible arrangements of these letters if we use only 3 of the letters at a time? Solution: I. Using I of theorem 5.4, we have 4 ways of arranging the 4 letters, i.e. we have 24 possible arrangements. 2. Using 2 of theorem 5.4, we have 4p3 ways of arranging 3 letters taken from the 4 letters, i.e. we have 24 possible arrangements. Example 5.9. In a class with 8 boys and 8 girls, in how many ways can the children line up if they alternate girl boy dash? 2. In how many ways can the children line up so that no 2 of the same sex are next to each other? Solution: I. The 8 girls can line up in 8 ways, and likewise the 8 boys can line up in 8 ways. For any single arrangement of the girls, all possible arrangements of the boys are possible, thus by Multiplication principle, we have 8, x8. Ways to arrange the children in girl-boy lines. 2. Now we must include the case of boy-girl. So we have 2x8, x8. Ways of arranging. Example 5.10, if I have 5 different books on my shelf, in how many ways can I arrange these books? Solution, we can arrange the books in 5 different ways, or 5x, 4x, 3x, 2x, 1 ways, or 120 ways. Remarks I, the number of permutations of n distinct objects arranged in a circle is n1. 5. This is because we consider 2 permutations the same if one is a rotation of the other. For n objects arranged around a circle, there are n rotations that give the same permutation. Dividing n by n gives n, 1. The 2 circular permutations below are considered the same, their order is A, B, C, D, E. 2. Permutations when not all objects are different, given n objects of which n1 are one kind, n2 are another kind, nk of another kind, then the total number of distinct permutations that can be made from these objects is n1, n2, nk. n. Example 5.11i, how many words, text strings, or distinct arrangements can be made from the letters BKOO? 2. How many permutations are there for the letters in the word banana? Solution, I. If we label the two O's as O1 and O2, and think of them as distinct, then the number of permutations is 4. For each permutation there will be a matching permutation that switches the O's, that is for O1 O2 BK there is the matching O2 O1 BK permutation. We can see then that if we divide the number of distinct permutations by 2, we have a count of the number of permutations of the 4 letters where we do not distinguish between the two O's. Therefore, there are distinct 4/2 text strings or 12 text strings. 2. If we think of all 6 letters as distinct, then we would have 6 permutations. As in the preceding example for the 2 n's, we would need to divide 6 by 2. For the 3 a's, we would have 6 counts for a single permutation. For instance, each of the following would be a single word if the a's were not distinct. A 1, a 2, a 3 bnn, a 1, a 3, a 2 bnn, a 2, a 1, a 3 bnn, a 2, a 3, a 1 bnn, a 3, a 1, a 2 bnn, and a 3, a 2, a 1 bnn. Hence the number of distinct permutations of the word banana is 62, 3. 6. Combinations, consider n different objects. This time we are concerned with counting the number of ways we may choose r out of these n objects without regard to order. For example, we have the objects A, B, C and D, and r equals 2, we wish to count AB, AC, AD, BC, BD, and CD. In other words, we do not count AB and BA since the same objects are involved and only the order differs. There are many problems in which we are interested in determining the number of ways in which our objects can be selected from n distinct objects without regard to the order in which they are selected. Such selections are called combinations or R-sets. It may help to think of combinations as committees. The key here is without regard for order. To obtain the general result we recall the formula derived above, the number of ways of choosing R objects out of n and permitting the chosen R equals n/nr. Let C be the number of 6 ways of choosing R out of n, disregarding order. C is the number required. Note that once the R items have been chosen, there are R ways of permitting them. Hence applying the multiplication principle again, together with the above result, we obtain C.R equals n/nr. Therefore, RnR NC. This number arises in many contexts in mathematics, and hence a special symbol is used for it. We shall write RnR/NCR NNR. Theorem 5.5, combination. The number of ways of choosing R out of n different objects, disregarding order, is given by Rn. RnR n. Example 5.12, how many different committees of 3 can be formed from Hawa, Sejanit, Nijasti, and Lensa? Solution, the question can be restated in terms of subsets from a set of 4 objects. How many subsets of 3 elements are there? In terms of combinations the question becomes, what is the number of combinations of 4 distinct objects taken 3 at a time? The list of committees HSN, HSL, HNL, SNL. Therefore, we have 4C3 or 4 possible number of committees. Example 5.13, a committee of 3 is to be formed from a group of 20 people. How many different committees are possible? 2. From a group of 5 men and 7 women, how many different committees consisting of 2 men and 3 women can be formed? Solution, there are 1,143, 17. 20. 320 possible committees. 353, 4. 7. 2, 3. 5. 3725 Possible committees. Remarks. I. N. RnR. N. 2. A set with n elements has two n subsets. 5.4 Probability of an event. Definition 5.5 The axioms of probability. Probabilities are real numbers assigned to events, or subsets, of a sample space. We can think of the assignment of probabilities to events, or probability measure, as a function between the collection of subsets of the sample space and the real numbers. Mathematically, a probability measure p for a random experiment is a real-valued function defined on the collection of events that satisfies the following axioms. Axiom 1. The probability of an event is a non-negative real number, that is, p, a, greater than or equal to 0 for any subset A of S. 7. Axiom 2. P, S, equals 1. Axiom 3, if A1, A2, A3, is a finite or infinite sequence of mutually exclusive events of S, then P, A1U, A2U, A3U, equals P, A1, plus P, A2, plus P, A3, plus, equals, PAI. It is rather surprising that with only these three axioms, we can construct the entire theory of probability. The next theorems and definitions help in assigning probabilities of events. Theorem 5.6 If A is an event in a discrete sample space S, then P, S, equals the sum of the probabilities of the individual outcomes comprising A. Theorem 5.7 Suppose that we have a random experiment with sample space S and probability function P and A and B are events. Then we have the following results: I, P, equals 0, 2, P, SE, equals 1, P, A, 3, P, B and AC, equals P, B, P, A and B, 4, if a subset of B then P, A, less than or equal to P, B. Definition 5.6 The classical definition of probability: if an experiment can result in any one of n equally likely and mutually exclusive outcomes, and if n of these outcomes constitute the event A, then the probability of event A is n P, A. Example 5.14 Consider the experiment of tossing a fair die. A fair die means that all 6 numbers are equally likely to appear. Calculate the probabilities of the following events: A equals 1 will occur equals 1 B equals even number will occur equals 2, 4, 6 C equals odd number will occur equals 1, 3, 5 D equals a number less than 3 will occur equals 1, 2 Solution: A, since the die is fair. 6 1, 2, 3, 4, 5, 6. 6 1, 1. P. PAP. 620.5, 630.5, 63B, P, B, CP, CD, PD. Example 5.1. 5.15. Suppose that we toss 2 coins, and assume that each of the 4 outcomes in the sample space S equals HH, H, T, TH, T, T, are equally likely and hence has probability 1/4. Let A equals H, H, T, and B equals HH, TH, that is, A is the event that the first coin falls heads, and B is the event that the second coin falls heads. Then, calculate the probabilities of A, B, AC, BC, and SC. The event that none of the outcomes will occur is the same as SC. Solution: 8. 1, 1, 1, 0, 1, 1, 0.5, 0.5, 1, 1, 0.5, 0.5. 0.542. 0.542. PS, PB, PA. PB. PA. CCC. Example 5.16. From a group of 5 men and 7 women, it is required to form a committee of 5 persons. If the selection is made randomly, then I. What is the probability that 2 men and 3 women will be in the committee? 2. What is the probability that all members of the committee will be men? 3. What is the probability that at least 3 members will be women? Solution: the total number of possible committees is 792. 5, 7, 12. 512, i.e. the number of possible outcomes in the sample space is 792. Let A be the event that the committee will consist of 2 men and 3 women. We need to know the number of possible outcomes favoring this event. The number of ways we can select 2 men from 5 men is 10 2, 3, 5, 2 5, and the number of ways of selecting 3 women out of 7 women is 35 3, 4, 7, 3 7. Using the multiplication principle, the number of elements favoring event A is 10x 35 or 350. Hence, using the classical definition of probability, 0.44 792 355 1. 23725. PA. 2. Let B be the event that all members of the committee will be men. Hence. 792.151. 20755. PA. 3. Let C be the event that at least 3 of the committee members will be women. Basically, 3 different compositions of committee members can be formed in terms of sex, 3 women and 2 men, 4 women and 1 man, and all are women. Hence the number of possible outcomes favoring event C using the principle of combination together with the addition principle is 350 175 21 546 570 547 153725. 9. Therefore, 0.69792. 546. 512. 570 547 153725. PC. Definition 5.7, Relative frequency definition of probability. If an experiment is repeated a large number, n, of times and the event A is observed n times, the probability of A is P, A, n. The above definition of probability is based on empirical data accumulated through time or based on observations made from repeated experiments for a large number of times. 5.5 Some probability rules theorem 5.8, if A and B, then P, A U B, equals P, A, plus P, B, P, A and B. Example 5.17, consider the experiment of tossing a fair die. Let A equals even number occurring equals 2, 4, 6, B equals a number greater than 2 occurring equals 3, 4, 5, 6, C equals odd number occurring equals 1, 3, 5 I. What is the probability that A and B will occur? 2. What is the probability that A or B will occur? Solution. We use the concept of set theory to help us solve probability questions very easily, and Venn diagrams are useful tools to depict the relations between events within the sample space. The shaded region on Fig 1. Shows the event that both A and B will occur. A and B equals 4, 6, thus P, A and B, equals 2/6. 2. A or B A U B equals 2, 3, 4, 5, 6 A and B equals 4, 6 hence, 3, 4, 2, 5. 6, 6, 6, 6 P A U B P A P B P A and B. Example 5.18, 60% of the families in a certain community own their own car, 30% own their own home, and 20% own both their own car and their own home. If a family is randomly chosen, A. What is the probability that this family do not have a car? B. What is the probability that this family owns a car or a house? C. What is the probability that this family owns a car or a house but not both? D. What is the probability that this family owns only a house? E. What is the probability that this family neither owns a car nor a house? Solution. Let A represents that the family owns a car and B represents that the family owns a house. Given information, P, A, equals 0.6 P, B, equals 0.3, and P, A and B, equals 0.2. A, required, P, AC, equals P, AC, equals 1 P, A, equals 1 to 0.6 equals 0.4 B, required, P, AUB, equals P, AUB, equals P, A, plus P, B, P, A and B, equals 0.6 plus 0.3-0.2 equals 0.7 C, required, P, and BC, U, AC and B, equals 10. P, and BC, U, AC and B, equals P, and BC, plus P, AC and B, equals P, A and B, plus P, B, P, A and B, equals 0.6 to 0.2 plus 0.3 to 0.2 equals 0.5 D, required, P, AC and B, equals P, AC and B, equals P, B, P, A and B, equals 0.3 to 0.2 equals 0.1 E, required, P, AC and BC, equals P, AC and BC, equals P, AUB, C, equals 1 P, AUB, equals 1 to 0.7 equals 0.3. We can represent various events by an informative diagram called Venn diagram. If properly and correctly drawn, a Venn diagram helps to calculate probabilities of events easily. The figure below shows various events represented by shaded regions. Note that the rectangle in each figure represents the sample space. 5.6 Conditional probability and independence. Conditional probability provides us with a way to reason about the outcome of an experiment, based on partial information. Here are some examples of situations we may have in our mind. A. What is the probability that a person will be HIV positive given he has tuberculosis? D. A spot shows up on a radar screen. How likely is it that it corresponds to an aircraft? In more precise terms, given an experiment, A corresponding sample space, and a probability law, supposes that we know that the outcome is within some given event B. We wish to quantify the likelihood that the outcome also belongs to some other given event A. We thus seek to construct a new probability law, which takes into account this knowledge and which, for any event A, gives us the conditional probability of a given B, denoted by P, A B. Definition 5.8 If P, B, 0, the conditional probability of a given B, denoted by P, A B, is /PB. PANB PAB. Example 5.19, suppose cards numbered 1 through 10 are placed in a hat, mixed up, and then one of the cards is drawn at random. If we are told that the number on the drawn card is at least 5, then what is the conditional probability that it is 10? Solution: let A denote the event that the number on the drawn card is 10, and B be the event that it is at least 5. The desired probability is P, A B. 6 1/6, 1/10. 5, 6, 7, 8, 9, 10. 10. 5, 6, 7, 8, 9, 10. 10 5, 6, 7, 8, 9, 10. /PPPPNPBPANBPAB. 11. Example 5.20, a family has 2 children. What is the conditional probability that both are boys given that at least one of them is a boy? Assume that the sample space S is given by S equals B, 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 G, G, B, G, G, and all outcomes are equally likely. B, G, means, for instance, that the older child is a boy and the younger child is a girl. Solution: letting A denote the event that both children are boys, and B the event that at least one of them is a boy, then the desired probability is given by 313/4. 1/4. /PB. PANB PAB. Law of multiplication. The defining equation for conditional probability may also be written as P, A and B, equals P, B, P, A B. This formula is useful when the information given to us in a problem is P, B, and P, A B, and we are asked to find P, A and B. An example illustrates the use of this formula. Suppose that 5 good fuses and 2 defective ones have been mixed up. To find the defective fuses, we test them one by one, at random, and without replacement. What is the probability that we are lucky and find both of the defective fuses in the first 2 tests? Example 5.21, suppose an urn contains 7 black balls and 5 white balls. We draw 2 balls from the urn without replacement. Assuming that each ball in the urn is equally likely to be drawn, what is the probability that both drawn balls are black? Solution: let A and B denote, respectively, the events that the first and second balls drawn are black. Now, given that the first ball selected is black, there are 6 remaining black balls and 5 white balls, and so P, B A, equals 6/11. As P, A, is clearly 7/12, our desired probability is 22. 7. 11/6. 12/7. P, A and B, P, A, P, B/A. Independence. We have introduced the conditional probability P, A B, to capture the partial information that event B provides about event A. An interesting and important special case arises when the occurrence of B provides no information and does not alter the probability that A has occurred, i.e., P, A B, equals P, A. When the above equality holds, we say that A is independent of B. Note that by the definition P, A B, equals P, a mathematical intersection symbol B, /P, B, this is equivalent to P, a mathematical intersection symbol B, equals P, A, P, B. Definition 5.9, independence. 2 events A and B are said to independent if P, a mathematical intersection symbol B, equals P, A, P, B. If in addition, P, B, greater than 0, independence is equivalent to the condition P, A B, equals P, A. 12.